have a ball here, and if I take this ball and hold it here, this ball will have gravitational potential energy. When I let it go, the gravitational potential energy turns into kinetic energy. Now, what that means is that if I know how much gravitational potential energy the ball has here, I also know how much kinetic energy the ball will have as it lands. Which means that I can calculate how fast the ball is going right as it hits the ground. Well, aloha, everyone. Today, we're going to talk about the law of conservation of energy. Now, it turns out when a lot of people hear this, they think about a concept called conservation of energy, and they say, oh, that means saving energy, right? And so, like, turn the lights off when you're not in the room. And that's not what we're talking about. In science, when we say a law of conservation of, and fill in the blank, it means that that object or that quantity cannot be created or destroyed. So in this case, the law of conservation of energy says whatever energy you start with, you have to end with. You might have heard of the law of conservation of mass in chemistry class, and it's the same idea. Whatever mass you start with, you have to end with. So mass cannot be created or destroyed. The same thing is true for energy. So here's the big idea behind it. The energy you start with, E sub I, is equal to the energy you end with. Whatever energy you start with is equal to whatever energy you end with. Oh, but sometimes energy flows into or out of the system. So if you have an external influence on the system, that external influence may put work into the system. So whatever energy you start with, plus any work, and remember, work is a change in energy. So if we start with this energy, we have this much change, that's energy flowing either into or out of the system in the form of work. Then we have a final amount of energy. So for instance, if I had a system that started with 10 joules of energy, we put 2 joules into it, we'd better have 12 joules of energy at the end. So let's try a fairly simple problem here. Here I am with a ball, and the ball happens to be 1 meter above the ground. And I want to know how fast will this ball be going when it hits the ground. Well, I can do this using kinematics. I could figure out the acceleration as it falls, and I could figure out how fast it's going at the end, and final velocity, right, and initial velocity, and I could use kinematic equations. But it turns out it's easier to think about this in terms of energy. Well, the math is easier. Here's what I mean. The energy I start with, well, what kind of energy does the ball have when I'm starting? Well, it's potential energy, gravitational potential energy. So it's going to start with gravitational potential energy at the beginning. So I'm going to put UGI for gravitational potential energy initial. There is nobody doing work. Once the ball leaves my hand, I'm not putting a force on it. So that means that there is no work in this situation. So plus work, that is going to turn into a 0. Is equal to, well, what kind of energy is it going to have as it runs into the ground down here? Well, it's got to be moving, so that's going to be kinetic energy at the end. So, final kinetic energy. It turns out I don't even need to know the mass of this ball in order to solve this problem, because you'll see something very interesting. You might remember that gravitational potential energy is equal to m times g times h. And you might remember that kinetic energy is equal to 1/2 mv squared. So I'm going to substitute those formulas into what I've written already. So this is going to be m times g times h. Oh, and I guess it's h initial, so at the beginning, is equal to the kinetic energy at the end is 1/2 mv squared. And I guess it's v final here. Now you'll notice something about this. You have mass on both sides of this equation. So as long as the mass of the object does not change, this and this are gone. And so now all I have to do is solve for the final velocity. I'm going to multiply by 2, and I get 2ghi is equal to vf. It would be squared, so I take a square root in order to get rid of the squared, and I get vf is equal to the square root of 2 times g times h initial. So this is equal to the square root of 2 times 9.81 meters per second times, and be careful when you write your radical here, make sure it goes all the way across. Don't let it stop before you're done with this. 1 meter goes here, and this is equal to v final. This is equal to, when I do this, I get 4.429 meters per second. And you can see that because there's a meter squared, because a meter times a meter is a meter squared, over second squared, and that gets square rooted, and we have meters per second. So this ball is going to be going 4.429 meters per second when we drop it from a height of 1 meter. Let's try another example. Let's imagine that we have, maybe it's a car. So here's a car. And this car has a mass of, let's make it 1,500 kilograms. And it's going to go up a hill. And so it happens to be traveling this way. Maybe it's going, I don't know, how about 20 meters per second at first. So this is the initial. And it's going to go up this hill. This hill is going to be a height of, I don't know, let's make it 30 meters. And he's, of course, not just going to roll up the hill. The engine is going to be pulling him up the hill as well. So the engine is going to do work as you go up the hill. The amount of work that's being done is, let's make it 5,000 joules. And I want to know how fast will he be going at the top. Okay, so we start from the law of conservation of energy. Whatever energy we have at the beginning, plus any work that goes into or out of the system, is equal to whatever energy we have at the end. Now, it turns out here at the beginning, it's pretty easy to see that the car is moving, so the car has kinetic energy. So, kinetic energy initial. Plus, in this case, we are doing work, so plus work is equal to energy final. Well, at the top, it's going to have gravitational potential energy because it has a height. But in theory, it's also going to be moving. So that means it's going to have two kinds of energy at the end. It's going to have gravitational potential energy at the end, and it's going to have kinetic energy at the end because it's also going to be moving. So now that I have this, I'm going to remember my formulas. And I'm going to say kinetic initial is going to turn into 1/2 mv initial squared. And we're going to assume he doesn't use enough fuel to change his mass significantly on the way up. Okay, plus work. If you didn't have work, remember work is equal to force times distance times the cosine of the angle between them. Or maybe you remember it as work is equal to force dot product displacement. Okay, so 1/2 mv squared plus work is equal to, so UG-F, the gravitational potential energy at the end is going to be m times g times h final. Plus kinetic energy at the end is going to be 1/2 mv final squared. Now, one pitfall here. A lot of times people want to make masses cancel. But it turns out whenever you have a plus or a minus in any of the thing, you have to be able to factor out in this case, a mass in order for it to work. Now, on the right side of the equation, I could easily factor out a mass because it's in both of these terms. So it would work. But on the left side, mass is in this term, but not that term. So that means that I cannot cancel masses in this case. You need to be careful about that. Remember, a term is anything separated by a plus or a minus or an equals. So in this case, there are 4 terms here. 1, 2, 3, and 4. And in order for something to cancel, it has to be in every single term in order to be able to do that. Okay, so now that we have this, we're going to, I guess we just got to start moving stuff around in order to look for V final. So it's going to be 1/2 mv initial squared plus work. I'm then going to subtract this to the other side, minus mg h final, divided by, wait, no, not divided by, yeah, divided by. In order to get rid of the m, I'm going to divide by an m. And then in order to get rid of the 1/2, I could divide by 1/2, or I could just multiply by 2 on top or on the side. I'm going to multiply the whole thing by 2 up here, and that's the same thing. And this would be equal to v squared. So in order to get rid of the squared, I've got to square root this entire thing. Bam. And then when I square root this side, that takes out the squared. So, okay, it's a little bit more complex, but we can handle this. This is equal to the square root of, let's plug in some numbers, 2 times 1/2 times the mass was, I think it was 1,500, yes, 1,500 kilograms, times the initial was 20 meters per second, and don't forget this needs to be squared. Close the, that needs to be squared. Close those parentheses. All right, plus the amount of work we do is 5,000 joules. Hope that was enough. Minus the mass of this thing is 1,500 kilograms times, kind of running out of space here. Let me slide all of this over. All right, there we go. 1,500 kilograms times 9.81 meters per second times my H final is 30 meters. Now, remember what I said about being careful with the radical, making sure the square root goes all the way over everything? If I leave it like this is wrong because I don't understand that I'm square rooting everything. This square root needs to go all the way across. All right, divided by mass on the bottom, and the mass was 1,500 kilograms. Let's see what I get. All right, so at the end, I get that his final velocity, oh, I forgot an F right here. That should have been V final the whole way down. V final is equal to 0.26, let's round that to 270 meters per second. So it turns out he barely makes it up to the top, and he's barely moving at the end of that. This device is called a ballistic pendulum. Here's what it has. It has this piece that kind of hangs on here and is free to swing back and forth. Then over here, we have a metal ball that is connected to this thing with a spring on it. So here's what I'm going to do. I'm going to start by taking this and compressing the spring. And there's a little latch here that will hold it in place, like so. Now I'm going to put this pendulum piece back up and make sure that I get this to hang there. And now it's free to swing around like this. You'll notice if it gets all the way over here, there's this little edge on it that will keep it from falling back. So I will now leave this like this, and we will fire this ballistic pendulum in 3, 2, 1. And you can see that the elastic potential energy in the spring turned into kinetic energy over here, which then turned into gravitational potential energy in this configuration. So that's really all there is to it about the law of conservation of energy. Remember, the energy you start with has to be equal to the energy you end with. And don't forget about work. Work changes the amount of energy that you have. So, mahalo for watching, and see you next time.